All right, so the first thing it wanted you to do on page 19 was to use this data table to make a graph of position versus time. So title, got to put a title on your graph, position versus time, or X versus T. Remember the letter X stands for position. Then you have to put scales. So I needed to get to at least 10 seconds, so I did every line was 2. And on the position axis, I did every line was 5, so I could get to at least 30 meters. You can see I scaled it out that way. Now, part B asks you how far from the starting point was he at 6 seconds, and how do you know? How far means I'm looking for a distance. So how do I know? I know that at 6 seconds, when I read the graph, his position is about 22 meters. And I know he started at 10 meters. So I have to subtract those two positions to tell me how far he went, which is about 12 meters. Now, part C, write a mathematical model. That means an equation to describe this curve. Curve is a general term for the graph. So we're going to use y equals mx plus b because it's a line. First thing I'm going to do is I'm going to find the slope. Change in y over change in x. I can see that he moved a total of 20.0 meters in that 10.0 seconds. So therefore, the slope of that graph is positive 2.00 meters per second. My y-intercept is the starting position right there, 10.00 meters. So I plug that in, and I say that the position is positive 2.00 meters per second times time plus 10.0 meters. Part D, was his speed constant over the entire interval, and how do you know? So look at that graph. The speed is the magnitude of the slope. Since I have a line, the slope is constant. Therefore, yes, the speed is constant because we have a diagonal line with a constant slope, and the slope is the actual velocity, not just the speed, but the velocity. Includes a direction in which he was traveling. Any questions on page 19 before we go to page 20? All right, let's look at page 20 then. Now, part A, make the position time graph for this skater. So again, title, position versus time. Scale out your y-axis, scale out the x-axis. I used the same scales I had before. I plotted my data points, drew in my nice straight line with a ruler. Part B, how far from the starting point was he at 5 seconds, and how do we know? So if I go to 5 seconds on the graph, which is halfway between 4 and 6, I come up and I go over, I see he's at 20 meters. He's at the 20 meter position, but he started at the 4 meter position. So when I subtract, actually I'm saying I'm at around 19 meters. So if I go to 5, maybe if I read that a little more carefully, yeah, not quite at 20. So I subtract and I get around 15 meters. So you have to show some kind of work to be able to get that. It's the difference in the positions tells me how far he traveled. Now, was his speed constant? I have a diagonal line. So yeah, the speed is constant because the slope isn't changing. And if I find its value by doing the slope, I have a rise of 15.0 meters over a time of 5.0 seconds. So this skater was traveling at 3.0 meters per second. Notice I don't have a sign on it because I asked for speed, which is a scalar. If you put a positive on this answer, it would be wrong. Part D, in the first trial, the skater was further along at 2 seconds than he was in the second trial. Does that mean he was going faster? And you should have said no, because when I say he was further along, I'm talking about his position. Your position, your location, does not tell me how fast you're moving. Speed tells me how fast you're going. So further along is your position. It just means you were further along on the number line at a greater position, not necessarily moving faster. All right, any questions on page 20? All right, let's go to page 21. Again, plot the position time graph for this skater. Title, position versus time. I scaled out my axes, similar to how I did it before. I did every line was 2 seconds. I did every line on the Y or the position axis was 2 meters. I have one diagonal line here, a horizontal line here, and another diagonal line here. So it says, what do you think is happening from 4 to 6 seconds? So 4 to 6 seconds is right here. I have a horizontal line. What does that mean? Yeah, he stopped. So he was not moving from 4 to 6 seconds because the position didn't change. We had a horizontal line on that graph. Part C, what do you think is happening from 6 to 12 seconds? That's from here to here. What did he do? Cam? Yeah, he reversed direction, went backwards, back to the starting point. And I know that negative slope means they changed direction. They went backwards. And they do go back to the starting point because I end up at a 0 meter position at the end. I'm back at the origin. Part D, find the average speed from 0 to 12 seconds. This was a little tricky to do because average speed needs the distance traveled divided by the time. So this skater went from 0 to 12 meters. So that's a distance of 12. Then they didn't move. And now they went backwards 12 meters. Distance doesn't care in what direction they moved. So it's 12 plus 0 plus 12. In other words, they moved a total distance of 24.0 meters. And they did that in 12.0 seconds. So the speed would be the distance divided by the time, 24.0 meters divided by 12.0 seconds, or 2.00 meters per second. Now, find the average velocity. The velocity does not use the distance. What does it use? Displacement. You look at the starting point and the end point. The starting position was 0 meters. What's the ending position? They start and end in the same spots. What is their displacement? How far out of place are they? So the displacement is 0 meters in 12 seconds. So to get that velocity, displacement over time, 0 divided by 12 is 0. Yes. Yep. Anyone need anything here first before I go back? All right. So you asked about this. Further along is talking about position. It asks, does that mean he's going faster? Further along is talking about position, not speed. That's all. Okay. It's basically vocabulary. Just understanding what further along means. Means you're ahead. All right. Anything else? Okay. You can use those pages to help you with the quiz. You'll probably need space for scrap paper to work things out. Keep out your reference table and your calculator as well. Our quiz today is in the Google Classroom again on the Chromebook. So go ahead and grab your Chromebook. We're now going to take the quiz on Unit 2D, which is actually about velocity time graphs. We didn't see those on the homework, so hopefully you studied. But go ahead and take this quiz now, please. Unit 2D. But again, you can use that homework to help you. While we're waiting for everyone to finish up the quiz, notice that tonight's assignment is 1 page in your packet, page 24. So make a note of that. Tomorrow we'll be taking a quiz on our next section of notes, Unit 2E, based on the homework. You'll be able to use the homework again to help you with that. Okay. All right, let's get started with section E of Unit 2. And Unit 2E is all about calculations with graphs of velocity versus time. Specifically, and uniform motion. Okay. Basically, the only calculation you'll be asked to do, or I should say calculations, from graphs of velocity time when we have a uniform type of motion are to either, 1, find a distance traveled, or 2, to find a displacement between 2 times. Okay. In either situation, I want to remind you that right now we have an equation on our reference table which could be used to do this. We only have one equation we've learned in this unit and checked off. So when we look at page 6 of our reference table, which is where all these equations are, we should see that this is the only equation we're using. Right? We can either use it for a speed or a velocity, and then we just change what the D is. It's either D or D with the arrow, depending on whether I want a speed or a velocity. So let's look at that for a minute. Let's say it's speed. That means I'm looking for D. What would I have to do to get the distance traveled? Multiply the velocity by the time, or the speed by the time, rather. Sorry, speed by time. Likewise, if this was velocity, which is displacement over time, and I asked you now from the graph to find a displacement, what would you do? Multiply a velocity by the time. Okay, so let's talk about where that comes from on a graph. I'm going to give you a graph. Let's make a graph and look at how we do this. This is a graph, a sketch of a graph of velocity in meters per second over time in seconds. So our title would be velocity versus time. And let's put two horizontal lines on this graph. There's a 0 velocity. Let's say this is at 5 seconds. And that time point there is 10 seconds. Let's say that this y coordinate is +3. And this y coordinate is -3. Okay, let's say question number 1 said, how far did the object move from 0 to 5 seconds? How far did this object move from 0 to 5 seconds? How far means I'm asking you for what? So my unknown is distance. Notice this is a given. What is this? That's a time. So I know I'm looking at a time of 5 seconds. But on my graph, I can read the speed, right? The speed is the number on the velocity without the sign. So look between 0 and 5 seconds. That is the velocity. What's the speed? Just 3 without the sign. Can you now find that distance traveled? Using what equation? V is d over t. We always start with the way it's written on the reference table, which means that the distance is the speed times the time. We can now do our substitution with units. So that is 3 meters per second times 5 seconds. Oh, don't worry about the sig figs right now. What does that mean the distance traveled is? 15 meters. The seconds would cancel. I'm not even going to worry about the check step right now. You should be able to do the check, the dimensional analysis. Does that make sense? Okay, we're going to do 6 questions with this one graph. Okay, that's question 1. Let's do a second question. And I'm going to do it on another sheet of paper so I can pull that graph back. Question number 2. How far did the object travel from 5 to 10 seconds? When I say how far, what am I asking you for? D. What is this giving me? That's giving me a time. So that's a G. And that time interval is 5 seconds long, isn't it? Okay, come back to your graph. In order to get a distance, we know we need the speed in this time interval, right? That is the velocity from 5 to 10 seconds, not the speed. What is the speed? What is it, Brandon? 3. Okay, without the sign. Without the sign. So in order to get the distance, we start with the equation on the reference table, and we move it around for distance. And then we do our substitution with units. And then we solve it. Normally we would pay attention to sig figs, but don't worry about it right now. What does that mean the distance traveled is? Okay. Question number 3. How far did the object travel from 0 to 10 seconds? How far means I'm asking you for what? Okay, here's the thing. When I look at that graph, I don't have one line between 0 and 10, right? How many lines do I have between 0 and 10 seconds? 2. To do this, it means I need to know how much distance was here and how much distance was here. And then what do you think I do to get the total distance? Didn't we already find the distances in each time period? We found it here and we found it here. So what am I going to do to get my final answer? Add them up. So the distance would be the distance from 0 to 5 seconds plus the distance from 5 to 10 seconds. That's what we have to do, is we have to just add those amounts, because Using the equation we have only works for one line segment on a graph, not for two. Means you got to find them for each time period and then add them. So what was the distance traveled from 0 to 5 seconds? What was it from 5 to 10 seconds? So what is the total distance traveled? 30 point meters. That's 3 of the questions of the 6 that I want to tackle with you from that one graph. Can I go on to another? Question number 4. What was the object's displacement from 0 seconds to 5 seconds? What am I asking you for now? How do I write that? I don't write it with a D. D with the arrow over the top. Means it's a vector. I'm going to need a direction on it. So if I think about givens, this is one of them. What's this? That's your time, which is how much time? 5 seconds. The other thing we need is the velocity over that time period. And where do I get that from? The graph. We read the graph from 0 to 5 seconds. What is the velocity? Positive 3 meters per second. We need the sign on it because that's our direction. So the equation we're going to write is the same one we have on our reference table, but with arrows to indicate we have vectors. But again, if I want to solve this for displacement, what is that equation for displacement going to look like? It's the velocity times the time. So now we can do our substitution with units. So the displacement is therefore positive 3 meters per second times 5 seconds. Don't worry about the sig figs, but what is the answer for the displacement? Positive 15 meters, or 15 meters. We're talking about left and right motion to the right. You could give me either answer and that would be accepted. All right, 2 more questions before we go to the packet. Number 5. What was the object's displacement from 5 seconds to 10 point seconds? Very similar to the last question, right? Let's use our guess method. What can I list as givens here for this question? Janelle? Is, yep, we have a total time length of 5 seconds. Ashley, can you give me the other given, which comes from the graph? From 5 to 10 seconds, what do I know? Think back to the last question. What did I get besides the time? Yes, what is the velocity? Negative 3 meters per second. All right. And what is our unknown? What are we going to write as the unknown here? Can you tell me? The displacement, or D with the arrow. All right. The equation is the same one because we only have the one equation on the reference table currently to work with. Velocity is displacement over time. So if I move that around for displacement, what is the equation? Velocity times time. All right, let's tackle our substitution with units. that is -3 meters per second times 5 seconds. So let's solve it now. Emily, can you tell me what the displacement is?
-15 meters.
Or?
15 meters to the left.
That's right. I have one more question. You ready for it? All right. I guess I'll do it on the back. What was the object's displacement from 0 to 10 seconds? Again, think about the graph. How many line segments do we have between 0 and 10 seconds? 2. You can't do it for 2 separate line segments. You have to figure out the displacement in each individual time period. And then what do you think you do to get the answer? Add them up, just like we did with the distances. You add up the individual values. So to get the displacement, we're going to take the displacement from 0 to 5 seconds and add it to the displacement from 5 to 10 seconds. And do we know these values? Sure we do. Nick Rennick, can you help me out? 0 to 5 seconds, the displacement was? 15 what? And what was it from 5 to 10 seconds? So what is the total displacement? What does that mean? What does a displacement of 0 meters mean? Yep. That's all it tells me. They went back to where they started. All right, I've got one more thing I want to talk to you about before we go to the packet. And that it goes back to the graph for a minute. Can I go back to the graph? Okay. Whenever we have lines on a graph, there's one of two things we'll ask you to do besides just reading the graph for numbers. Like here, we read to get the velocity, and we also read the coordinates to get speeds. In the past, we've done slope calculations for lines, right? Anytime we have a line on a graph, sometimes we'll ask you to do a slope. This kind of a graph, we don't do a slope for. Not yet. That will be our next unit. Right now, however, the other thing that we can do is we can find a product of two things. Think about what we're doing. Here is the velocity, which is this line, and here is the time. And when I multiply those two things, I'm getting this in here. I'm finding that. What is that I would be finding? I'm multiplying a base by a height. That's an area. So the area between the velocity and time axis is displacement. That's the displacement. And this particular shaded area, that one I just shaded in, that is the displacement from this time to that time. 0 seconds to 5 seconds. I'm going to shade in another area. Here's the line, and where's the time axis? Above it. If I shade in there, what's that shaded area going to be? It's still a displacement because I'm multiplying a velocity value by a time value. But what would that red displacement on my picture represent? The displacement from There you go. Okay. And it's exactly the same thing. This is the height, and that's the base. That's the height, and that's the base. It's a rectangle. You're finding the area of a rectangle. Okay, graphically, that's what you just did. But that's where that equation comes from. It's an area calculation. All right, let's go to our packet. And let's look at page 22. We're going to use those notes to help us out. This is the page after the homework you did for today. This is a motion map. Tomorrow we're going to learn about these, how you can create them yourself. But what you have here in this motion map, this is a number line. That's your x-axis. Each hash mark vertically shows you another meter on the number line. And each of these arrows represents the velocity of the object. It's showing you the speed of it and the direction it's moving in. The dots are telling you where the object was located at 1 second time intervals. Okay, so based on this, what can you tell me about how this object is moving? Can you tell me anything based on that?
Moving in a positive direction.
Yep. What else can you tell me about it? It's moving to the right, which is the positive direction. Can you tell me anything about how it's moving to the right, Janelle? And why do you say that? That's not what would tell me. This is not a graph. This is just a number line, like a measuring tape. The speed is the length of the arrows. Nick, what do you think? Constant. What's constant about it? Yeah, it's speed and its direction of motion. The speed is the length of the arrow. And aren't they all pointing in the same direction? So the direction of motion is also constant. That means the velocity is constant. So what can we conclude about it? That this is moving to the right with a constant velocity. All right, let's look at part B. Part B says draw a qualitative graphical representation of the position versus the time. Qualitative means no numbers. In other words, can you just describe what the shape of this graph is going to look like? If you're moving to the right at a constant velocity, what does the position time graph have to look like? If you don't know, you have your notebook there. You should be able to tell me. Moving to the right with a constant velocity, what's that graph going to look like? Do you know? More than a diagonal line. If you are traveling to the right, Cam, there you go. It's got to have that positive slope. The positive slope tells me it's going to the right. If the slope were negative, what would that tell me? It was going left. These arrows would all be reversed. So let's just go ahead. Any diagonal line with a positive slope on here is good. There we go. We need a diagonal line with a positive slope. All right, what would the velocity time graph look like for this type of motion? What's the velocity time graph going to look like? Again, no numbers. You're traveling to the right with a constant velocity. Brandon? There you go, a horizontal line above the time axis. Here's the time axis. So pick a value, I don't care what. There's no numbers. It's got to be a horizontal line above the time axis. The fact that it's a horizontal line not on the time axis means the velocity value is the same at all the times. It's constant. The fact that it's above the time axis tells me it's traveling to the right. Those were patterns we discussed yesterday. Let's now go to part D. Write a mathematical expression that represents the relationship between position and time. In other words, I want an equation. Can you write the equation, therefore, for this graph of position versus time? It's a line. What are all equations of every line. Start with that and then change all the letters out. What's on the y-axis of this graph? What does the slope of a position time graph represent? Name it. The velocity. What's on the x-axis of this graph? Time. So velocity times time plus. Do you remember what the B is? Or initial position. Tells me what your initial position is. Since I don't have any numbers, I can't put values in, but I can say what those values would represent. Let's now do the same thing, a mathematical expression, an equation for the velocity time graph. Again, it's a line. What's on the y-axis of this graph? Velocity. All right, look at this graph. M. What is the M, the slope of this? This one is 0. What is 0 times anything? So let's just drop it out. It's gone. It's 0. So what's the y-intercept? Initial velocity. In other words, your velocity is constant. Your velocity at any time is equal to the initial velocity. It's not changing. All right, describe what the area under the curve here represents. If I were to shade it in, let's shade it in. What is that area that I'm shading in right there? What does it represent? Name it. Area on a velocity time graph. We have this in our notes. We just did this a minute ago. The area on a velocity time graph is equal to the what? What? I heard, yes. It is equal to the displacement. That area is the displacement. Very good. Okay, let's look at page 23. All right, I'm giving you a data table of positions and times. Can you make a graph of position time here on this axis right now? Let's start it. We may not get it finished. We'll finish it tomorrow before your quiz. But let's get started, shall we? So I've got all the times and the positions labeled, so I just got to plot the points. 0, 0, 1 at 2, 2 at 4, 3 is also at 4, 4 is at 7, 5 is at 10, 6 is at 10, 7 is at 10, 8 is at 5, 9 is at 0. You're going to have multiple line segments on this graph. I don't know if you can see them. I have one here. We have another one here. We have another here. Let's just get those line segments drawn in. Another one here. And then finally, we have one right here. And we'll pick up with part B of this question tomorrow. Okay, folks? Page 24 is your homework for tomorrow. Have a great day.